Hello, class. So on this video, we'll finish out the part of section 2.5 that I'm covering, being autonomous differential equations. Oh, and I misspelled something here, I realize. So in the previous example, we were looking at how to draw a phase portrait for a differential equation, an autonomous differential equation. Now we saw that, and this is the picture that we drew in the previous example, that a phase portrait tells us three key things of information about a differential equation. Technically four, if you count equilibrium solutions as part of the information you get. Okay? So what information do you get from the phase portrait? First, okay, as I mentioned, if you want to count them, you know what the equilibrium or constant solutions of the differential equation are. Okay? Those are the horizontal asymptotes. Two, you know on what regions will your solutions lie on, right? Because as soon as one solution has, as I mentioned, solutions stay in the region that they are in. So for example, this solution y equals g of x in gray, as soon as we know that it passes through the point 0, -1, it has to stay on the interval y equals -2 to y equals 0. That's one of the facts I gave you about equilibrium solutions. So they partition the xy plane, specifically the y-axis, into regions where your solutions stay in, your non-equilibrium solutions. Okay. Next, you learn whether the solutions are increasing or decreasing, right? Because you can solve for, well, just tell whether your derivative is positive or negative on each of the y intervals, and that tells you that the solution are increasing if the interval has a positive derivative, or decreasing if the interval has a negative derivative. Finally, since solutions have to approach horizontal asymptotes if possible, then this also tells you the long-run behavior of solutions. Now, there's one more thing I forgot to say. It's not going to be very important for us because it's just like something that equilibrium solutions are called, but let me just mention it here. Notice that the equilibrium solution, y equals 0, has solutions approaching it from above and from below, right? Solutions that lie on the y interval y equals 0 to y equals 2 approach the horizontal asymptote y equals 0 as x grows really large in the positive direction. For solutions that lie on the y interval y equals -2 to 0, as x grows really large, those solutions also approach 0. Such solutions are called stable solutions. So again, I won't actually write it as a formal definition. It's just something I want to tell you in case you read it somewhere else. So you can think of this, another word they're called is an attractor. So think of this as attracting solutions as x grows really large. You can see that in the picture. On the other hand, if the equilibrium solution has other solutions getting very far away from it as x grows really large, then it's called a unstable solution. And an example of one is y equals 2. Why? Well, look at what happens with y equals 2. As x goes really large, solutions on the y interval 0 to 2 grow away from the equilibrium solution y equals 2. Solutions on the interval 0 to 2 to infinity also grow away from y equals 2 as x grows very large. And in this situation, you would call such a solution an unstable solution. So y equals 2 is an unstable solution. Or you can think of it as a repeller. So it repels solutions as x grows very large. Finally, in the case that an equilibrium solution both attracts and repels, which I don't have one in this example, but if that is the case, then such a solution will be called semi-stable. Right. So if on one side of the equilibrium solution, the solutions are getting close to it, but on the other side, they're getting far away from it. So in other words, since there are only three possible cases, if an equilibrium solution is not stable, or semi-stable or unstable, it is called semi-stable. Let me fix that. Okay. So just one other thing I wanted to point out. They're not definitions I'm going to be focusing on, because what's important is the information that you get from the phase portrait. What names you give the equilibrium solutions. I mean, it's important in the sense that if you want to explain this behavior of a equilibrium solution attracting or repelling, the easiest way to do it is by giving them names. But other than that, what's really important for me, and I think in applications, is can you draw a phase portrait that's going to give you this general information about your solutions. Okay. Last thing I wanted to say, now let's just do one more example. Draw a phase portrait for the autonomous differential equation dy dx equals e to the y minus 1 times y minus 3. Again, this only works for autonomous differential equations, so I have to make sure that whatever's on the right is only an expression involving the variable y, which is the dependent variable, and constants. Here you can see that that's the case. You have dy dx on one side by itself. On the other side, we only have y variables or constants. Okay. So you can do a phase portrait. As I mentioned earlier, or following the process we did in the previous video, in the previous example, first find the equilibrium solutions. So this is your f of y. Okay. So first, to find equilibrium solutions, solve f of y equals 0. So for us, that is e times y, e to the y minus 1 plus y minus 3 equals 0. Whenever you have a product equal to 0, just as in the previous example, the only way this is 0 is if each of the factors is 0, right? So if you remember that from college algebra, from this you get the equation e to the y minus 1 equals 0. From this you get the equation y minus 3 equals 0. So what are the solutions to both of those equations? Well, e to the y minus 1 equals 0. Well, you can either, add y to both sides, take the natural log, or you can just see that, oh, e to the 0 is 1. Right? So y equals 0 makes e to the 0 equal to 1. 1 minus 1 equals 0. So the equilibrium solutions are so from this one, we get y equals 0. From this one, we get y equals 3. Now, what I'm going to do right now is instead of, or you know what, let's just draw the phase portrait now and then get the other information. Okay? So let me draw so just to follow the same process we did in the previous video. Draw the xy plane. It's good to label the axes. And then plot your equilibrium solutions. Again, they're horizontal asymptotes. So this one is, so you don't have to name them. I think it's good if you do. So this one is y equals 0. Then we have y equals 3. So let's do 1, 2, 3. Oops, sorry. Let's make that more readable. So y equals 3, and then y equals 0. We have our equilibrium solutions. Now, again, these partitions, are y interval into regions. You don't have to give them names, but this is region 1, region 2, in this case, 3 regions. All right, so it implies we partition the y-axis into 3 regions. Okay, so region 1, and you don't have to name them in this order. Usually you read negative to positive, so that's why I'm doing it in this order. So you have region 1, which is the interval negative infinity to 0. Region 2, which is the interval 0 to 3. Region 3, which is the interval 3 to infinity. Now, just pick a y value in each of these intervals and plug it into the equation to see whether you get something that's positive or negative. Okay? So let's see, on the interval negative infinity to 0, we can pick y equals 1. plug it into the equation. Right? So the equation is, you're plugging it into f of y, right? Whatever is on the right-hand side of the equality. So we have e to the 1 minus 1 times y minus 3, y is 1, so 1 minus 3. And again, you're not interested in what this is as a number, just the sign. Oh, I hope I didn't use equals. Yeah, I didn't use equals. Good. Okay, so e to the 1 is 2.781 something, so that's positive when you subtract 1 from it. 1 minus 3 is negative. Positive times negative implies negative. So we know that our functions are decreasing on this interval, or on that subregion. Now let's pick something between 0 and 3. Oh, shoot, I should have done -1, right? Sorry. Yeah, so 1 is not in this region. -1 is. So let's go ahead and make sure this is right. So now things change a little bit, because e to the -1, that's less than 1, right? So when you subtract 1 from it, that's negative. -1 minus 3, that's negative. Negative times negative is positive. Man, so I did a bunch of mistakes, but I actually drew it right here, right? So we have our derivative being positive on this region, meaning that the solutions are increasing. Okay, now here we can choose on the interval 0 to 3. Here we can choose y equals 1. That's in this interval. And the work is the same as what I erased before, right? E to the 1 minus 1 is positive. 1 minus 3 is negative. Positive times negative is negative. So solutions are negative on this interval. Finally, let's pick something on the interval 3 to infinity. Let's say we picked y equals 4. Plug it into the differential equation, or f of y. So we get e to the 4 minus 1 times 4 minus 3. E to the 4 is minus 1 is positive, 4 minus 3 is positive. So this is positive. So what do we get? Well, our solutions are increasing on this interval. Finally, just so you can have all the information easily readable, you can just plot one solution in each subinterval. How do you do that? Just pick any point on the interval. So you can pick the point, for example, 0, 1, and then draw the solution using the information you have. This solution has to be increasing and has to be approaching the horizontal asymptote. Same on the left-hand side, or for x values less than 0. And then you can use the same color for everything. That's perfectly fine. Here we can plot the solution 0, 4. Oh, it's decreasing, sorry. So decreasing, so as you draw it, you have to be moving your pencil lower, right, as you go from left to right. And it has to be approaching the asymptotes. Okay, so it's going to look something like that. Now, on the interval y equals 3 to infinity, now the solution is increasing. So it has to look like that for x values greater than 0. For x values less than 0, increasing looks like that, and it's approaching the horizontal asymptote. Finally, pick any other point here. You can pick the point, for example, 0, -1. Now in this interval, again, the solution is increasing as you go from left to right. So it's going to look like that. And this is a face portrait. So if I ask you in the exam, draw a face portrait, this is what I want you to draw. This thing right here. And that's it. That's how you draw a face portrait. Sorry about my typos, drawing things in the wrong way and saying that it's negative when it's positive, but hopefully you understand. Everything now looks correct. Okay. So that's it. That's face portraits. Again, you gain a lot of information without actually having to find the solutions. Now, in the next videos, we're going to go into a more general version of this. It's going to be more complicated, so we're going to have to use software. In particular, we're going to use Mathematica. So I already know that at least one of you has been able to download Mathematica successfully to their personal computer. So please download Mathematica as soon as you can, as soon as possible. I'll send a message about this in a message through Wire Courses later. But please try to download it. If you have any issues, please let me know, and we can try to work it out.